Allison. I'm recording. I'm Ben Walker. I'm the head tutor for digital circuits. I'm going to be doing a test review section on the chapters or presentations 8 and 9 for Dr. Bossi's class. The plan for today, I'm going to go over the slides, and I've also curated some example problems which I made up for this that we'll look at after I'm done reviewing the content he's prepared for you guys. So chapter 8 is on data path components. Firstly, they're just going over various number representations. So the sum here is basically telling you that we can represent a number by a string of digits multiplied by various weights, which can give you binary, which can give you decimal, which can give you octal and hexadecimal. So really, just to convert between these, it's pretty simple. To go forwards from binary to decimal, you're going to multiply by each weight, by each number. So basically, this is the ones place. This is the this is the 2 to the 0 place. This is the 2 to the 1 place. And once you go to the other side of the decimal point, you start counting downwards. This is 2 to the -1, 2 to the -2. And this way, you can actually represent fractional components in binary with radix R. These are two algorithms for converting between radix and between decimal. They use successive modular arithmetic. So we can kind of look at this example here. So for converting 3 3/8 into binary, what you're going to do is you're going to do successive division. So first off, the question is, apologies. Okay. I don't remember this slide.
Just convert it to binary.
Yeah. So to convert to binary, the first question, well, how I take this is look at the left of the decimal place and look at the right decimal place. So from the left, we're trying to figure out the most significant bit. So here, we're trying to convert 3 into binary. 3 in binary is 1, 1. And we can also look at that in a different way by taking the floor of each number and comparing it to modular 2 arithmetic. We can find that D0 gives us a 1 and D1 gives us a 1, which is the 3. Likewise, when you go into the right side of the decimal point, we can use the same modular arithmetic trick to find that we have a 0 for the 1/2 place, a 1 for the quarters place, and a 1 for the 1/8 place. Which tells us that this is 11.011, which is 3 3/8. Note when you do this trick with numbers that aren't a perfect power of 2, for example, something that's like 1/2 or x over 4, x over 8, x over 16. If you, for example, have something that's x over 3, x over 5, something that's not a clean power of 2, you'll typically have repeating decimal places, which you can kind of treat the same as repeating decimals in decimal notation. Okay, so for converting to octal and hex, the procedure is pretty much the same, but you're going to group the binary digits together. For example, here we're converting this to both octal and hex. So octal is grouped in groups of 8, should be 8, and hex is grouped in 16. Wait, yeah. So octal has 3 bits and hex has 4 bits. So to do the conversion, you start at the decimal point and you look in groups of 3, and if there's no digit to the left, we can add a leading 0, and likewise when you look to the right, if there's no digit on the right, you can add a trailing 0, and that allows you to convert each number into their quote-unquote decimal sections. So this is a decimal 2, this is a decimal 6, but when the in the octal representation, these convert directly to the string of binary. For hex, you actually end up having values that are greater than decimal can hold. So for example, if you have a 10, you don't write a 10 in hex, you write an A, and you get A, B, C, D, E, and F in hex corresponding to 1 to 15. So once you start having decimal values over 10, you need to switch to letters. All right, so there's 4 popular ways to represent signed numbers. You can do a magnitude, sign, 1's complement, 2's complement, and XSB. 2's complement is the most common. You'll see it used a lot because it's really, really convenient. With 2's complement, you can add signed negative numbers and positive numbers. You can do subtractions without having to do any extra operations to them. XSB is really common for floating point numbers. I'll get into that later, but it allows you to set a bias, and you can represent lots of numbers pretty succinctly with XSB. So sign magnitude is probably the first idea you'd come up with when trying to figure out how to represent numbers. Basically, you just put whether the number is positive or negative at the leftmost bit, but it's not very efficient as you have 2 values for 0. To do operations on these, odds are you'd just look at their magnitude and then add them or subtract them. To represent the numbers, you just find their magnitude and then add the sign bit. 1's complement is a little bit more advanced. It negates every single bit of the number to get the negation. Because of this, we actually have 2 zeros as previously. We have 0, 0, 0 and 1, 1, 1. This is a positive 0 and a negative 0. And to do a subtraction or addition with these 1's complement numbers, you also have to add a 1 while doing the operations. This way you can get the correct answer. With 2's complement, you don't have to add the 1. 2's complement is beautiful. It's asymmetric, but the numbers work out very, very well. And this is the most common form of signed integers that you'll see. XSB is not as clean. You're basically defining the number as the difference between a bias and the actual number. So for XSB, it's not very clear. There's typically not like a signed bit. You have to compare the number to the bias every single time that you want to figure out what the number is. But it's very, very convenient for floating point operations where we will typically see a range of exponent values and we compare them to bias. But we'll get into that later. Okay, as I said before, typically for operations, for subtraction, you typically just negate the number and add it. This is very, very simple in 2's complement, but it's not very straightforward in other representations of signed numbers. As I'm saying here, for magnitude, just change the sign bit. Okay. This is for 1's complement. So you can see here you have to add a 1 after your operation if you're using 1's complement. So it's not a very straightforward process. However, if you have 2's complement, you don't have to worry about adding +1 because it's already in the numbers representation. And this is a very natural way to represent signed integers. All right, so to detect overflows, you have to figure out if the bit into the carry does not equal the carry out. Hello. So basically, you can see that for 2's complement numbers, all you have to really look at to detect overflow is if the output value makes logical sense. So if you're adding 4 to -5 and it gives you -7, that's not the logical answer that you'd find. You'd find -1. But here you can see that the overflow has occurred when you're adding these 2 numbers together. Yep. So let's talk about adders and subtractors. There's a lot of components that go into building these, but the most basic one is the half adder. Half adder can take 2 inputs and it can calculate their carry and their sum. But itself, it cannot be used to create cascaded adders. This is because the half adder doesn't have a carry in. So to create a full adder, what you do is you take 2 half adders and you connect them together with an OR on the carry out, and this allows you to create a full adder. These full adder blocks, the truth table can be shown here. It has 3 inputs and it gives you the carry out and the sum. for those three inputs. Full adder is a crucial electronic component, and it's used to create lots of circuits. As I said before, 2 half adders make a full adder. Here we're looking at the number of gate delay. Not totally crucial. So here we can see that we can cascade our adders together to do ripple carry operations. So if we wanted to add 2 binary strings together, what we are going to do is we're going to take each component of the binary strings and we're going to place them into each full adder. And the operation flows from the right to the left. So these A naught and B naught operation has to occur first, and then this full adder computation, the second one, can occur. And these carryovers are basically exactly what happens when you do rote arithmetic by hand, or when you find if you have something that's greater than can be represented for that binary digit, you end up having to add it to the next digit. And this method allows us to pretty easily and succinctly add 2 numbers together, but it has a drawback, which is the gate delay. So you have to wait for the add value to cascade through every single full adder till you get your final result. So that means as you go farther to the left, like the third sum of the carry out, you end up with a large gate delay. The propagation is on the order of n. Okay, so that's how you build an adder for an arbitrary number of bits. To do a subtractor, all you're going to do is you're going to negate the input prior to addition. So typically you'll do this in 2's complement. That way you don't have to do any more operations. Yep. So this is an example of a subtractor. As I said before, you're taking the 2's complement negation of B, and then you add them together, and that gives you your subtraction. Similarly, this is an incrementer circuit. It's adding 1 to the input. So you can see here, these is a ripple carry. A1, A2, A1, A naught are all given to one of the operands. And then to represent the input, the incrementing, we're giving a 1 to the carry in of the first adder, and it propagates through and adds 1 to the string. Similarly, you could add it as a 1 as the B naught input, and with no carry in, they basically do the same thing. If you wanted to add 2, then both these would have to be 1. Okay. Let's say you wanted to control whether or not this was an adder or subtractor. What would you have to do? Basically, you'd have to control whether or not this is the right one, right? Yeah. So you have to control whether or not it receives the inverted string or the non-inverted string. So the way that it's typically done in circuits is you're going to simultaneously compute the inverted and the non-inverted string, and you're going to use a mux to select the inverted or the non-inverted one to feed forward into our adder, which is done here. And finally, if you wanted to detect the absolute value for a 2's complement number, it's not totally straightforward, but we can do that with adders. So to calculate the absolute value of a number, all we have to do is we have to invert it if it's negative. So the first thing is we have to detect the sign bit, which is actually the most significant bit for the unsigned representation, and we can use that to control whether or not each of the other bits gets inverted. And finally, because it's 2's complement, we also have to add 1. So what this will do is if it's a positive string, which means that this leading bit is 0, it just returns itself. But if the leading bit is 1, it's going to do a 2's complement inversion on all of the remaining bits in order to return the magnitude, which is kind of cool. So we're kind of building up an ALU here. We have addition, we have subtraction. Another important thing is equality and comparison. So equality is pretty simple. Here we have a NOR gate, which basically tells us whether or not the inputs are the same. So the truth table If it's 0, 0, it returns a 1. If it's 1, 1, it returns a 1. But if it's 1, 0 or 0, 1, it returns 0. These allow us to check for equality. So that means if this bit is the same as this bit, whether it's a 1 or a 0, it passes a 1 into this final AND gate. So what this is really asking is, are all of the bits of this string equivalent to all of the bits of this string with this final AND gate? So that's kind of how you check whether two binary strings are the same. You can also do this iteratively. This costs an increased amount of delay, but it's also somewhat simpler for space reasons. This is really the same thing as previous, but instead of it all going to one AND gate, it's kind of like a cascade sequence of AND gates. So you can see here, we only need one of these strings not to equal each other in order for the output equal to be false. So if these two are equivalent, these two are equivalent, these two are equivalent, we pass a 1 onwards and we AND it with itself. But if for any one of these cases, if they are not equivalent, they are going to be ANDing a 0 into the string. And if we AND a 0, that means our output has to be 0, because 0 is always going on ANDs. Okay, so to do a comparator, basically we're using Boolean logic to do it. So this takes 4 inputs, 4-bit words into each one, and it calculates whether or not they are equal, greater than, or less than. I don't think we need to go quite into the details of derivation, but if you had a truth table and you had a K-map, you'd be able to rederive all of these. The important thing is whether or not these inputs are enabled, we enable these outputs. And these comparators are very useful when we're building in ALU. Okay. Finally, we can cascade these together. So to do a 12-bit comparator, we actually take our input enable bits and we tie them to the outputs of the less than or equal than's, and that allows us to compare bigger and bigger words. So for example, if we wanted to do a min-max circuit, we're basically going to use the comparator to determine whether one number is bigger, and then we're going to use the output of that comparator into a mux to select the bigger or the lower one. Okay. So here we have, let's say we want to select the minimum of x and y. Okay. So x and y both go into the comparator, and if x is bigger than y, it returns a 1. And if we want to return the smaller bit, we want to end up returning y if this output is 1. And if it's 0, we want to return x. Okay, so that can go into our mux. And if it's a 0, it returns x. And if it's a 1, it returns y. And we can actually control the parity of the output of the comparator by using an XOR gate to the min-max. This XOR gate basically allows us to switch the output of the comparator from a 1 to a 0, which basically allows us to select whether or not we're selecting the maximum or the minimum. You can see the truth table here for a little bit more clarity. Okay, so as I said, with all these pieces, we can build up in either ALU or arithmetic and logic unit. The simplest idea to implement one of these would be to simultaneously compute every single operation that we can do with A and B, and then just to select what we want with the mux. It seems like a great idea, but there's a lot of wasted space and a lot of wasted power in an implementation like this. So modern ALUs typically use a bit slice design. The best way to think about bit slicing is that a lot of these operations can be done with an adder, right? So if we wanted to, for example, we wanted to compute A, just returning A. It's the same thing as adding A to 0. Okay, so these are the inputs into our adder, and this is the logic we want to compute. Likewise, subtraction is as long as we negate B before we add them together, we can compute subtraction. We also compute as the input to adder, we can compute Boolean ANDs, Boolean ORs, Boolean XORs, and all we have to do is add them to 0, which means we only have to use one adder to implement all of these various logical components. But that does mean that we have to have these input components ready to be selected before they go into the adder unit. But integrating this adder reduces the space complexity of our circuit by a lot. Yep. Let's talk about shifters. It's the operation you can do either a left shift or a right shift. You'd also do an arithmetic left shift and a logical left shift and a logical right shift or an arithmetic right shift. I'll get into the details later, but you can basically see here that the flow of data is shifted to the left for each of the input lines. We actually ignore the input 3 here. Because we're shifting to the left, we actually need an input. If this were a circle left shift, we'd actually feed I3 into this input line, which would allow all of the data to be kept the same. Sorry, all the data would be preserved during this left shift circular operation. I guess it'd be a ring shift. So if we wanted to shift by an arbitrary amount, what's the best way to do it? This is called the barrel shift arrangement. And what we basically do is we represent the shift in binary. And once again, we're using powers of 2. And the important thing to note is if we do 2 consecutive shifts together, they kind of add together. So if we have a module that does 4 left shifts, 2 left shifts, and 1 left shift, and we can independently control each shift register, that means we can control any arbitrary binary value between 1 and 7 to do left shifts by. Okay, so we want to left shift this number by 5. 5 in binary is 1, 0, 1. So we take 1, 0, 1, and we put that into the enable registers for the shift registers, for the barrel shifting. And that allows this number to be shifted by 5 successively. Okay, and this decreases the number of wires rather than using a specific shifter for every single number we might want to shift. Instead, we can represent the number in binary and save space. All right, this is where it starts to get complicated. This is an arithmetic left shifter. Arithmetic shifts are a little bit more complicated than logical shifts. Arithmetic shifts try to preserve the sign bit on the left while the left shift operation occurs. That allows them to be used for division. So what we have here is the left shifter is exactly the same as we mentioned previously with this barrel shifter arrangement. We take the input 5, which gives us 4, no for the 2's place, and a 1 that gives us 5 to the left shift. So it takes all the inputs and shifts them to the left. But because this is an arithmetic shift, it needs to preserve the sign bit. And it does that via the right shifter arrangement. Shifters can be used to implement things very, very quickly. For example, if you approximate everything to be a power of 2, you can turn what would be a complicated multiplication division algorithm into the summation of various left shifted signals. It's pretty convenient and pretty fast as well. Okay, let's get into multiplication. Multiplication is successive addition, as you learned from elementary school. This is the exact same algorithm you'd use to multiply 2 decimal numbers by hand. What you do is you multiply this multiplicand row by the multiplier, and you place it right there, and then you add an additional 0 for every bit shift to the left. You add another 0 here, and you add them all together at the end to get your product, which is pretty convenient. And we can actually implement this exact same algorithm with arrays of adders. So this is mathematically equivalent to this multiplication algorithm by hand. You can actually see that the left shifting happens automatically, and this is literally adding the numbers and carrying them over exactly as we've seen previously in that hand algorithm. Okay. This is looking at the delay time. The delay increases the more you go to the left, which is kind of the same as the ripple adder. when you're dealing with signed numbers, you have to put ones as your leading digits because ones are the same as zeros when you're working in 2's complement space. Great. So multiplication by a constant, it's the same as left shifting if it's a power of 2. But if you wanted to do something that's offset by a power of 2, there's actually a more efficient way to do it. You can actually write this as, you can actually distribute. So if we had a times 2 to the k plus p, that's the same as a times 2 to the k plus a times p. So that way you can actually add the left shift of k, sorry, the left shift of a by k bits to the product of p times a. And that would actually save a lot of space and make the multiplication a little bit more efficient. Okay, let's talk about counters. If we take a number and we add 1 to it successfully, congratulations, that's an up counter. The same thing for subtraction. This is the exact same as we've seen previously counters in this course, as you're basically traversing along a graph for each step. Okay. Counters can be for non-powers of 3. So this one counts up to 2 and it goes back to 0. So it has a period of 3. There's a lot of different ways to implement counters. This is a ripple counter. For some reason, the flow is from the right to the left in this slide. I want to design it that way. But essentially, these toggles act as clock dividers. So every time the clock comes, it's going to toggle the signal. So on the rising edge of the clock, it toggles, but it doesn't untoggle into the rising edge of the next clock. So that actually divides the clock by 2 every toggle. And then if we feed the output of this to the clock input of the next counter, it's going to also divide, it's going to treat the output of the previous one as its new clock, which means it's also going to divide by a power of 2. So every single T flip-flop can act as a divide by 2 counter. So if you wanted to slow a signal 8 times, we would have 3 ripple counters in a series. Yep. We can also do this another way. So this has input delay, which kind of builds up. As I said previously, the same with multipliers and adders. As you go further to the left, there's larger delay for the input. We can build this entire thing in parallel. It's a little bit more complicated because you have to figure out the exact D or T inputs as a function of the current state of the finite state machine. It'd be kind of something that you did on the previous exam. The benefit of this implementation is there's far less propagation delay, but it costs a little bit more space to have all these additional logical gates. Yep. This is just another representation of it. Okay, what's another way to do this? We can actually just add 1. So if we have in a full bit adder, we can simply add 1 every clock cycle. And once it comes up to its maximum value, this would be 15 for 4 bits. Sorry, it'd be 7 for 4 bits. It would overflow, and which would give us this TC, this toggle output as the overflow, and it would reset back to 0 once it counts up to the largest value. Okay. This is just adding a little bit more logic to the previous one. Okay, so here we're doing a free running modulo 16 counter. So this is operating on the previous examples that we've seen, where we're basically adding 1 each clock cycle. These mod 16 counters have 4 load inputs, and if we, they have 4 load ins. So basically, if you change nothing to the default operation, it operates as a 16-bit counter. But if you give values to these load ins, and you give the loadout to the TC input, every time it counts up to its maximum value, instead of going back to 0, it pulls the data from the load in, which allows you to count between X and between 15. Likewise, if you want to count between 0 and x, you can actually take the outputs and you can do Boolean arithmetic on them back to the clear signal. So this one, once it counts up to 9, the clear signal becomes high, which means on the next clock cycle, it's going to reset back to 0. If you put this back to the load signal, you could actually count between x and y being any arbitrary numbers between 0 and 15. Okay. So you can actually sync these two things together. TC is kind of like the overflow signal. So once C0, C1, C2, C3 all become 1, the next clock cycle it counts up to 0, and TC is kind of an overflow. So once TC hits 1, it goes to the CNT of the next mod 16 counter, which allows it to begin counting. So this is a way to cascade these two counters together. But an important thing to note here is that the clock is shared between these two things. There's actually no cascading of the clock, so it's not like we're taking one of these divided signals and making it the clock for the mod 16 counter. Instead, we're using a shared clock, and we're actually telling the mod 16 counter when it's allowed to update. This makes them synchronous, and it actually decreases the propagation delay for the counter configuration. Okay, if we use a direction bit, we can actually mux our outputs and we can determine whether we're counting up or counting down. And as I mentioned previously, we can use this for clock division. So if we have, once again, 2-bit divisors, we can divide our clock into lower frequencies. So if you want to divide this by 256, we're going to use an 8-bit count-up counter, which would divide it, divide by 2 to the 8th. So this is using 8 2-bit dividers. Or it's counting up to 255 every single time. So different ways to look at it. Okay. Let's talk about probably the most complicated mathematical part of this, which is number representations, particularly floating point. So fixed point is what we saw previously, where our binary point is the same, and we're able to just do normal math, but with negative exponents. To do math on these, we just have to line up the binary point and do the computation. As previously we've seen these kind of computations.
You go from the right to the left, right, for the 0.3? So like whatever number this second digit is.
Yeah, okay. So it's using qn.f. So n is the total number of bits, f is the number of fractional bits. So if it's 8.3, that means we have 3 to the right of the decimal point, and we have 5 to the left of the decimal point. So we just align that up the decimal points. And we add leading and trailing zeros as necessary. So it's the same thing for multiplication. We just line up the decimal points. And when we're done, we have to add up the decimal points and do rounding if we want to put it into the same number of bits.
You pad with the most significant bit, right?
Sorry?
You pad with the most significant bit.
Yes. Yeah. Okay. So floating point is probably the most complicated little thing. So it's a really useful way to represent numbers, but it is relatively complicated. So there's typically 3 parts to floating point numbers. You take the sign, take the exponent, and you take the mantissa. The sign bit tells you whether it's positive or negative. The exponent gives you the kind of like the scientific notation of the number, whether it's extremely large or very small, which means floating point numbers can be used for a variety of number sizes. And the mantissa is basically in scientific notation. That's the number being multiplied by the 10 to the power of your exponent. The mantissa contains the most information and just tells you, what is the specific value of your number. Typically, we work with a normalized version, which means the mantissa does not include the leading 1, which we'll see in a second. This leading 1 is implicit. Yep. So IEEE has the single and the double. The single takes 32 bits, the double takes 64 bits. To convert these, we're going to use this formula, literally directly use this formula. It'll give you the right answer every single time. You can see here that the exponent in the single uses a bias of 127. And for the double, it uses a bias of 1023. Okay. Once again, to convert from IEEE to decimal, we literally use this formula directly. But to convert from decimal to IEEE, you have to write it as decimal string, and then you ignore the leading zero, and you get the mantissa as everything else, and then you count how many movements of the decimal point it takes you to get to replace the decimal point with mantissa. That's your exponent, but the exponent is written in bias, which means we have to add 127 to it if it's positive. Sorry, in every case we have to add 127 to it. That way we can have a negative exponent represented with a normal normal binary word. So when it's negative, we're adding 127 to a negative number, so we end up still with a positive exponent value. Okay. So adding these two things together, it's not very easy. First up, you have to line up the decimal points. So the best way to kind of line up the decimal points here is to look at the difference between the exponent values. That tells you how many ways, tells you how you have to move the binary point, the decimal point. So if they have the same exponent, the difference is 0, they're already aligned. If one is a little bit bigger, this one's in case by bigger by 1 bit, you have to shift the smaller one. Sorry, we have to shift the bigger one 1 bit to the right to make up for it. And once we shift it, we can add the mantisses normally. Okay, but because we're using the same number of bits to represent all these numbers, we're going to have to typically cut off information. So here it works out that there's a lot of trailing zeros, so we can fully represent all the information. But for example, if we're adding 800 trillion to 1e to the negative 20, right? Like something nano, something like mega, typically information is going to be lost. And that mega is way more important than that nano. So typically they get cut off in the trailing zeros. So finally, we calculate the, so the output exponent is just going to be whichever one was bigger. And then we renormalize our mantissa. And then we, sorry. Oh, yeah, sorry, I was confused. So typically, if we don't have to, if we have our mantissa in the exact same format as previously, you just pick the larger exponent. In this case, it's E1. But in the case where the mantissa requires an additional bit to the left of the decimal place, or additional 2 bits to the left of the decimal place, we have to return it back to its original format. So here, when you add these together, you ended up with 2 bits to the left of the decimal point. What you have to do is you have to shift the decimal point 1 to the left, and to do that, you actually have to add 1 to your exponent. Okay, so that's kind of how you do the addition. Multiplication, it's the same. Well, it's very similar. So you multiply the mantissas and you actually add the exponents. So it's kind of the same as multiplication in scientific format. Let's make this bigger. Yeah, there we go. Should have done this a while ago.
Oh well.
Yep. So we have an example here. We're adding the products together. Sorry, we're adding the exponents together, and we're subtracting 8 because that is the bias, and we're multiplying the mantissas. When you multiply the mantissas, you end up with a lot more bits than if you were to add them together. Fortunately, in this case, it's all rounded off rather well, actually. But in normal situations where there's not all these trailing zeros, you're going to have to lose information to do these computations. So that's lecture 8. Go over lecture 9, which is a lot shorter, and then I've got some example problems to go over quickly. Okay. So previously, logical components have been black boxes. They give you the correct output all the time. Sometimes they have delay, depending on the specific problem, but the actual electronics of them have been kind of concealed. We're going to look into that box. So the two common transistors that we're using in CMOS logic devices are the NMOS and the PMOS. Okay. One is basically connects the drain and the source when the input is low, and one connects the drain and source when the input is high. And they're called PMOS and NMOS. And when they're used together, it's called complementary metal oxide semiconductor, which is called CMOS. Okay, so this is a CMOS inverter. Okay, we have a PMOS on top and an NMOS on bottom. And basically the question to ask yourself in these circuits is the output being pulled up or is the output being pulled down? Okay, so here we can see that when the input is 1, okay, the PMOS thing, I like to think of this little dot as the inverter, right? So when the output's a 1, the inverter is low, which means this is open. Okay, so there's no connection to VDD, but there is a connection to ground. Okay? So when the input's 1, the output is pulled down to ground. Conversely, if the input is 0, the PMOS becomes connected, which pulls our output up to 1, and the NMOS remains open. So that's how you kind of invert signals. And the cool thing is we can use a slightly more complicated stuff to do logic. There's not a great way to do directly and and ORs, but it's really simple to do inverted ands and inverted ORs. Basically, the same logic applies here. Okay. If A is 1 and B is 1, okay, the signal is being pulled down. Okay. If either A or B is 0, the signal can't be pulled down because one of these is an open, right? But if at least one of these are 0, if A is 0 or B is 0, it gets pulled up. Okay, that's the exact truth table for AB naught. Okay, the only time AB naught is 0 is when both inputs are 1. Okay, conversely, if we wanted to do the OR, it's kind of the opposite logic. So here it's being pulled up only when both A and B are 0, and it's being pulled down when A or B are 1. Okay. So we have to make a determination between the analog realm of input voltages and our binary 1s and 0s. So basically we use a notation to figure out where we define 0 and where we define 1. So we basically define zones for which the output can be considered 1 and for which the output can be considered 0. When you're in between those two zones, it's considered undefined, which hopefully means that the logic is in the process of switching to a defined state. If your output is continually in an undefined region, that means your device is broken and it's bad. Noise margins, they basically tell you that how much space you have against noise. So if our signal is noisy, it can go into these undefined regions and it can be bad. Yep. So static power is related to the leakage. So if A and B are constant and the output is constant, there's still energy being flowed into the system. The impedance between the gate and the source of the MOSFET isn't infinity. So there's some leakage current that's always flowing through these whenever the device is on. So that's considered the static power. It doesn't change. It's always constant. But there's dynamic power, which is often called the switching power, and it's related to the capacitance of these gates. So when we switch between a logic 0 and a logic 1, we have to charge and discharge all the capacitances in the circuit, and that costs energy. Okay. There's also fan out and fan in. For circuits, fan out is crucial. If we don't have the ability for fan out, we don't have the ability to do arbitrary logical computations. So fan is super important. We'll talk about output capacitance in a second. Fan in is also useful. We can have more inputs to our gate, which allows for more logical combinations. Okay, this is just rise time, fall time. Just more about delays. And here you can actually measure, for example, if you want to find the fall time, you'd find the 90% value and the 10% value. So here's the 90%, here's the 10%. Now all you do is measure the time between it. Yep, and it's the same thing for the rise time, is between the 1% and the 90%. Okay, so gate delay, the critical path is the worst case. Okay, so here we can see there's two paths. One is takes 7 gate delays, one takes 8 gate delays. The 8 gate delay is the critical path. Okay, the gate delay is affected. The decent model for it is intrinsic delay, load dependent delay, and total load model. I'm going to do an example of this in just a second. This is the last slide. We're going to pull it up. So let's say here we want to find the delay of the critical path. Okay. Basically, the first thing to look at is which one goes through the most gates. The path from C to Z goes through a lot of gates, right? It goes through gate 1, you could go through gate 3, and it goes to gate 7. Okay. So these slides give us a formula for the gate delay. They tell us the intrinsic delay in nanoseconds, and they also tell us the delay associated with the load capacitance for each gate. So for gate 1, okay, we have the intrinsic delay of 0.05 nanoseconds, and we also have this load dependent delay, which is really okay. So for gate 1, we have to look at fan out. Fans out to the 2 input OR. It fans out to a 3 input OR, and it fans out to a 2 input OR. Okay, so here's the 2 input and 2 input. It also fans out twice to this 3 input OR. So we have to put a 2 for the capacitance. Okay, because it hits the gates twice. Okay, and then we add all these together and we find the total load capacitance. Okay, once you have the total load capacitance, you can multiply it by this little constant, and that allows you to get the total delay. So it's the load dependent delay plus the intrinsic delay, and that gives us the delay for the first gate. So the same thing is true for the second gate. So the second gate in 1 to 3 to 7 is the 3 gate. Fortunately, it only has one output load. Okay, so the capacitance of this 3 input AND is 20 femtofarads. Okay, so we use the equation from here, this 0.34 for this. Yeah, for this one, right? It's a 0.34 plus 0.22 CL. So we take the 20, we multiply it by this. We add it to the 0.34, and we find 0.78 nanoseconds for gate 3. Finally, for gate 7, we're using the same equations as before, but the slides tells us that we're assuming a fan out of 4 knots at each output. Okay, so 4 knots has a capacitance of 40 femtofarad, and what you can do is multiply it by this equation, 0.38. You're going to add to the intrinsic delay. That gives us a 1.22 nanosecond delay for gate 7. So the total delay for this critical path is going to be delay 1 plus delay 3 plus delay 7, or 3.58 nanoseconds. Yep. So I have 2 other examples to go through. Sorry, 3 actually. So now we're done with the slides. We're good to the examples. Let's say we're tasked to design an AND gate with CMOS. Okay. Right now we have 3 examples that we've seen. We have an inverter, we have a NAND, and we have an OR. Okay. There's no direct way to implement AND or OR with just 4 transistors. what we need to do is we need to take the output of the NAND gate and bring it into the inverter. Okay. So you can see here, this is the NAND gate, which gives us A times B, and we have to invert it. So we bring it to a CMOS inverter, which brings us the A times B. So it actually takes 6 transistors to do an AND computation. The same exact thing is going to happen for OR, where this is the top and the bottom of this is going to be switched, and that's going to compute the NOR signal, which will be inverted for the output. Okay. And finally, what if we wanted to build a 3-input NOR? Okay. So here's the NOR gate. Okay. It's all about pull up and pull down logic. Okay. So we want the output to be pulled up only when, So yeah, we want the output to be pulled up only when all of the inputs are 0. Okay. So here, only when A, B, and C are all 0 does the output equal B to D. Okay. Because these are in series. Likewise, we use our NMOS to figure out when we need to pull down. We're going to pull down anytime A or B or C is 1. Okay? So that way, where A, B, or C is 1, it's going to be 0, which is quite literally this. And anytime all of them are 0, the output's going to be 1. So that's how you do the 3-input NOR with CMOS. So finally, the last example I have is a floating point multiplication example. I'm using new numbers from the slides. So the overall form is you're going to find the product of the mantisses, and you're going to add the exponents, and you're going to subtract the bias. Okay. I attempted a by hand binary multiplication. I got most of the way, but I got tired. So I put in a calculator, and this is the output that we get. But you can see here, we actually end up with some digits that can't be represented with 8 bits. So our mantissa is only 8 bits long, which means we can have one leading bit, which is implied. We can have 8 bits to the right of it. Okay, it means we can only look at these 8 bits. We have to throw away everything to the right. Okay, this is part of the game, unfortunately. And we didn't have to add anything to the mantissa because we don't have to add anything to the exponents because we don't have to move this decimal place when we look at the final version of the mantissa. Okay, to look at the exponent, all we have to do is add them together, and we have to subtract 8. Okay, so this number is a binary 13. This is a binary 6. 13 plus 6 is 19. Minus 8 is 11. 11 binary is 1011. Okay. So for the product, we keep the sign bit the same. We're giving just these 8 bits with the implied 1 for our mantissa, which go right here. And finally, we have 1101, which is our 11 for the exponent. Just kind of how you multiply them together. Yeah, that's all the information I've got. Yeah, absolutely.
So you truncated it, or did you like round?
I truncated.
Just truncated?
Yeah.
Okay.
I'm not sure what the IEEE format, whether they recommend truncation or rounding.
Because Basu did something in class where he rounded.
I think rounding would make sense. But here, if you were to round, it'd be a round down.
Still a 0.
Yeah. But yeah, I think that if this were a 1, right, and you had everything else ignored, I guess you could round that up, and that'd be a 1 0.
1 0.
Yeah.
And then here you shifted this decimal point over. Did you have to account for that in the exponent?
So this is the 1 second. No. So there's one leading bit here, and there's one leading bit here. So this is where the decimal point would be directly after the computation.
Okay.
So yeah. So yeah, you add the number of spaces to the left. So you end up with a 0 1. If this were a 1 0, then we'd have to shift to the 1 to the left, and then you have to add 1 to the exponent.
Okay.
But here,
sounds good.
we just have to cut off the leading 0, so we're not
You're
touching the decimal place. Yeah.
Thank you.
Yeah, no worries. Is there anyone online? Probably not. Cool. I'll stop the recording.